This is IAT806 Lecture 7, and the topic today is recursion. So this segment is actually going to be comparatively short, mainly because the topic itself is another one of these abstract topics which takes a little bit of mental effort to wrap your mind around. So I'm going to show the concept with some visual examples, and we'll talk about this interesting thing called recursion. So today's excitement, as I suggested, is about recursion, and in the context of writing programs, the notion of recursion is kind of illustrated in this diagram that we're showing right here. Basically, the way it works is that a function does something very interesting. It calls itself. And you might think, oh, okay, so it calls itself, and then somewhere in that code, the function has to call itself. Where does it stop? And the answer is, inside a function that is designed to call itself, there is also needs to be part of that function needs to say, oh, wait a minute, don't call myself no more, we're done. And so that's illustrated here visually. We're seeing, you know, the function kind of embodied as a stick person. And that stick person is calling itself, which is in turn a stick person, which calls itself, which is in turn a stick person, which evaluates, oh, I'm done. So, and then inside the bubble, there's some values that are being computed by the stick person that's not being explicitly shown here, that are returned to the caller, The concept is that during the process of recursion, you're taking incremental steps towards a solution to some kind of problem by breaking it down into two subproblems, and you're delegating those smaller subproblems to another instance of the function that you're already in. So that sounds a little confusing, so let's move forward and show an example with a very simple little problem called factorial. So recursion is basically means calling a method from inside itself, as I've said already. So here's a method that calls itself. The method is factorial, and what factorial is, if you remember perhaps from mathematics class, is that factorial is that notation where you have a number followed by an exclamation point, okay? Number followed by exclamation point, and you know, so 4 exclamation point, and what that means is 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So you could see that 6 factorial is 6 times 5 times 4 factorial, because 4 factorial is 4 times 3 times 2 times 1, and it's 6 times 5 times 4 times 3 times 2 times 1. So you can see that each version of factorial is that number times one number less factorial. So here it is, the embodiment of that reasoning in a piece of a very short piece of programming code. So if you call factorial with some integer that's greater than 0, right, and greater than 1, because multiplying by 1 gives you the same value, then what it does is it returns the number times factorial of n minus 1. Okay, so 6 factorial equals 6 times 5 factorial. That's what we've got going on here. That's where the 6 goes. Here's 5 factorial because it's 6 minus 1. And so anyway, that's the recursive end of things. What's the stopping condition? The stopping condition is right here. If n is greater than 1, it continues. If n is 1 or less, like if you called it with a negative value, then it would return 1 right away. So that's on the else clause, not the elf clause, the else clause of this if statement. So if you call it with factorial 1, you return 1 right away. If you call factorial negative 3, you return 1 right away. Even though I don't recall, but I think, you know, factorial of negative numbers is not well defined. So let's show how this thing functions in practice, because, you know, you have this kind of weird feeling of, wait a minute, a function that calls itself, how can that work? So let's show how that can work. So here we're calling factorial of 3, well, not 6 this time, because there's not enough space for 6. And we say int factorial of n, and in orange I'm putting the kind of the actual values that are in place. So we're calling it with n equals 3, And therefore, if n is greater than 1 is the condition, 3 is greater than 1, so return n times factorial n minus 1. How would that be evaluated? That's n minus 1, 3 minus 1 is 2, and so therefore we will call factorial with a smaller value, n equals 2. And n is greater than 1, so we're going to call this factorial again with n equal to 1. So we have a function that calls itself, and we get to this one here on the right, and we've run out of slides. That's the big hint that there's a stopping condition just about to occur. N equals 1, so the if condition is if n is greater than 1, that's false, so therefore we go to the else part of this if statement, and we return 1. So what happens there? That thing fires, and it computes 1 and returns it to the caller. And I'm just using this arrow as kind of the conduit for the return value of the function. So, okay, so 1 is going to be put as the result of calling factorial n minus 1. There it is. So, okay, n times 1. Well, n in this case is 2. So 2 times 1 is 2, and we're going to return that to here. There's 2. And then there's that's 3 times 2, because this was called with the value 3, and that's returning 6 there, 3 times 2. So what we've seen is a function that can call itself, which is pretty cool. So in order for any of this stuff to work, we need something very important, and that's called a base case. And that's what the little stop sign in the little stick figure animation is about. It's a case or a condition that returns without further recursion. Recursion has to stop somewhere. If you don't have a stopping condition, let's say you constructed a recursive function, if you don't have a stopping condition, the function will just keep calling itself and calling itself and calling itself infinitely. So you need one to stop things. By the way, infinitely in computer terms does not literally mean infinitely. Basically what will happen is somehow or other we'll run out of resources. I'll get to that in a bit. And that resource will trigger an exception flag of some kind within the code, and the operating system will go, this thing's hogged all the resources on the computer. Something must be wrong. Let's kill it. Okay, so let's have in any case, the stopping condition is known as the base case. It is a case or condition that returns without further recursion, as I said, and it stops the recursive chain. In our case of factorial, what happens is the stopping condition was a value of n equal to or less than 1. So it returns 1 when n equals 1. If you're calling it with positive numbers, the stopping condition is when n decreases down to 1, so it's n equals 1. And in all the other calls, assuming positive values of n, the recursion essentially subdivides the problem of factorial by multiplying the number that it is parameter times a factorial call to n minus 1, a number smaller by 1. So the base case in this situation is where n equals 1, and that's the point to stop, because there's no point in going any further. Okay, so before I do this web crawling thing, one of the things that I've kind of mentioned on the way here, but I'd like to emphasize right now, is that the concept of recursion is primarily to chop down the size of the problem domain step by step. Okay, and in the web crawling thing I'm about to show you, that is also the case, that we're chopping the size of the problem into smaller and smaller pieces. In the factorial case, how to do it kind of suggests itself, right? I mean, it's fairly straightforward, because you can observe how 6 factorial is 6 times 5 factorial, et cetera, et cetera. And other recursive processes, similarly, it's taking incremental steps towards solving a problem, cutting the problem into a smaller piece. And in the case of writing recursive programs, the smaller problem is just like the main problem, just less bulky in some way or other. And when you're making that recursive, building a recursive program, you have a plan in mind as to how it is you're going to put these elements of solutions together, multiplying 6 times 5 factorial, and aggregate all those solutions together through this recursive calling procedure. So the basic concept is you're chopping the problem into smaller pieces and solving each of those problems step by step. The thing that's funky about it is, of course, is the function calling itself. So let's get on to another example. In this case, the recursive shape, as it were, is no longer just kind of a straight line. It's kind of tree-shaped, and we'll show you that in a second. So consider the task of web crawling. What is web crawling? Well, the idea, this is something that used to be, kind of more popularly known a number of years ago. This is the process by which you point a machine or a program at a web page, and what you ask the program to do is to locate all the HTML links in the web page, and you follow each of those links and read all those web pages that the links point to. In each one of those pages that you read, you gather up all the links, and then you follow all the links in all those web pages, you read all the pages, you gather those links, and you just essentially crawl throughout the entire web. That's what you hope to happen. Now, the reason why you would want to do this, or that an entity would want to do this, is to get a database of the entire web as linked from other elements of the World Wide Web. And this is the thing that search engines are doing every day behind the scenes. It's a lot more sophisticated than what I just suggested to you, but the basic concept is go to a web page, get all its links, follow those links, grab those web pages, grab their links, follow their links, grab those web pages, and on, ad infinitum, not literally infinity, but, something close to doing everything. And, search engines like Google and Bing and so on go out and search all this stuff and gather up a database of everything that's out there. Now, clearly, there's an enormous amount of stuff that is being stored in Google servers. When I was, I was in grad school when the web was first introduced, and I, like many people, I thought, geez, I wish there was a way to find things that was easier than clicking on links. The way in which, in the earliest days, the first web browser, Mosaic, did that is that Mosaic was written by a bunch of people, including Mark Andreessen at NCSA in Illinois. He built his browser, and one of the things that they did is they maintained a dictionary of all the web pages that were known at the time, which at that time was, dozens and then hundreds and then thousands. It started being every web page, and then it started to be web pages for organizations, because otherwise it would be just continue to get and grow and grow and grow. Now, so you could go to NCSA's web page, and then you could go and say, I wonder if there's something, do a text search within the browser inside that web page in order to find something about, cats or something, the primary, internet topic. And then, go find the cat web page. You click on that page and you can find things. It required human intervention to do that. So I had this, idea. I thought, well, geez, wouldn't it be great if that was somehow automated? My idea was about copying that and, doing something like web crawling. But I immediately got stymied by the concept of, wow, given the fact that the web is exponentially growing, you'd need an enormous amount of storage to store all this stuff. Yeah, that sounds insane. There's not enough storage in the computer systems at my university to do that. So I thought, whatever. I just, moved on to other things and continued to do my research on virtual reality. But a few folks around the world actually said, you know what, let's try to store it and see what it's like. Let's just see how demanding this task is. And it turns out the task is, it does take an enormous amount of storage, a problem that is being solved with money, but it has a real payoff, because what Google and others discovered is that, if you provide this service, everybody will come to you in order to get this service. And they tied it to a commercial purpose, which is, the first stuff being shown in the Google search is ads. And they're making money off the ads, among other things. Okay, so underneath all that, there's this technology of parse page, or web crawling. So what the parse page does, getting back to the slides now, is first reads on HTML, finds links. That's easy to find. You know, a well-formed link is easy to find. You have to go through parse the page once. That is to say, look for the, you know, anchor tag, pick off the URL it's pointing at, and then per link call parse page. So once again, recursively, you call parse page, and it recursively calls parse page on every link that's in the page that it is parsing. So let's show an example. So let's say you start with some page. Bam, page 1. It has some links. It has 4 links. I haven't shown it to you yet. And parse page is calling this, and then it runs into the link that points at page 2, reads in that page, and parses page there. And then the next link, it parses that page, page 3, page 4, page 5. So that's it. That's what it's doing. That's the first round, in that it is reads in page 2, reads in page 3, reads in page 4, reads in page 5. And then calls parse page on page 2 to read in its links. And then it goes off and reads in page 6 and page 7, and page 8 and page 9. And then that's it. It has run out of links. Another thing that I'm doing behind the scenes is I have a base case, and I'll ask you to think about what the base case is that I am putting in place here. Then it runs out of links here, returns to page 2, it's consumed all its links, returns to page 1 and says, okay, now let's take a look, continue on with page 3. Reaches pages 10 and 11, and then it runs out of those pages, goes to page 4, reads 12 and 13, runs out of links, goes back, reads page 14 and 15. Now, so what I'd like you to do now is I'd link you to think, that makes no sense. I'd like you to think about what is the stopping condition for all this? What is the base case, or what are the base cases? Because there might be more than one. So what I'm going to do is I'm going to have one of those dull video pauses, and I'd like you to think about what the stopping condition is. Okay, so that was a big enough gap so that I could, make sure I catch it. So what's the base case? Well, one of the ways to limit something like this that is potentially infinite, where, it's finite but it's gigantic, is to count the number of recursive calls so far. So pass as a parameter to parse page, how deep am I? So with the first one, it starts with 0 or 1, take your pick. And every time parse page is called, you increment that number and pass that as a parameter to parse page. So the first call, going back one slide now, wrong way. So this one, the depth count is 1. This one and this one and this one and this one, each of the depth counts there is 2, 1 plus 1. And here the depth count is 3 for all of these ones. And the outcome of that will be that you explore no further than that depth. So that's a so-called deepening strategy. And you might have noticed that when I first introduced this suite of web crawling pages, I went 1, 2, 3, 4. And in some sense, what I was doing there is I was saying, okay, only go to depth 1. Find out how far you can go with depth 1. And then go to depth 2. And so I did what's called iterative deepening. I explore to the depth of depth 1, and then I increment that number and then say, okay, now go all the way to depth 2. There's some more storage required for that in the background, but essentially the concept is pretty much the same. Okay, so remember, if you don't have a base case, you will get infinite cats. And so this is a web page that is out there. It's called infinitecat.com. It had been around for a long time, for about, I think, maybe 15 or 20 years. It has recently been bought by a cat product company, and they've kind of wrecked it. But anyway, it starts off it's at some point in the early 2001, 2002 or something, with a picture of a cat looking at a flower, and the person who hosted this took a picture of his cat or her cat, posted it online, and then said, okay, now get your cat to look at the picture of my cat on my web page, and send me a picture, and I'll put that picture online. So we have what you see here is there's a cat. He's looking at a cat, and the cat is looking at a picture, a picture of a cat on a monitor. This cat is looking at a picture of a cat on a monitor, which is there. And this cat is looking at a picture of a cat on a monitor, which is there. And that cat is looking at a picture of a cat on a monitor there. Something like that. And it keeps going all the way back to the base case, when the base case cat is Freddy, who's looking at a flower. Okay, so think about it. What is the base case here? Okay, so you might have thought, well, yeah, you gave it away with your words earlier. One of the base cases, of course, is you just simply get to the end of the recursive chain. Here's another question. Getting to the end of the chain, which is the first recursive cat picture, the starting point. So you can keep, in the original version of this, you got to look at the picture of the latest, most recent cat. In the current version that's online, if you go to infinitecat.com, you get the starting point of the chain, where the process started. And the fun thing about Infinite Cat is you get to see a lot of kitty cats, but the other thing that's interesting about it is you also get to see the evolution of equipment that people have at home. And so in the early days, you see lots and lots of CRTs, which is what this thing is. I think this is a CRT. No, actually, that's a flat screen. But earlier on, you see, CRT after CRT after CRT, and you get to see the evolution of, CRTs, disappearing because they're big and bulky and heavy, and they consume a lot of power, and getting replaced by flat screens, starting small, getting larger and larger. Okay. So here's the other question I was about to ask before I interrupted myself is, can you see all the cats in this picture? Think about that. Okay, so now that you've thought about, can I see all the kitty cats? The answer is no. And the reason why is, although physically, if we were looking at reproductions of images that were like real life, we might theoretically be able to see, 1,500 cats in this list, but practically we can't. And the reason why is that we have an array of pixels. We have a finite rectangular array of pixels, and each pixel has a red, a green, and a blue value that is in the range of 0 through 255. So every time you take a picture, the previous cat has been shrunk down onto a finite array of pixels. And that previous cat has been shrunk down to an array of pixels. And what happens is that the image gets smaller and smaller and smaller. And as the image gets smaller, it gets more and more quantized spatially, in X and Y, and probably a little bit in color too. So eventually what happens is it gets so small that the cat image ends, that's 6 or 7 layers back in time, gets down to 1 pixel. And everything further back in time is also on that 1 pixel. So you can't, there's the kind of the cutoff point there in terms of resolution of the image. So the other thing is that this thing of an image that contains an image of itself is called the Droste Effect. The original version of this that begat the name is this thing called Droste's cacao, or it's a, cocoa for putting in your coffee, making hot chocolate from. And this was designed by Jan Misset in Holland in 1904. And here is the Droste package, and she is carrying a cup of hot chocolate and the Droste package on a tray. And that's a picture of her carrying a Droste package on the tray. So here's at least 3 layers of Infinite Cat, and this is infinite, none on the Droste package. And you might think, well, thank you for the 100-year-old example. But wait, there's more. I have a 700-year-old example. So this is something called the Stefanschi Triptych. It's cut off a little bit at the top. And basically what's going on in this picture, and this is something, a triptych, which is a piece of religious art that used to be in St. Peter's Basilica. It was in the old basilica. The thing is still there, but it's somewhere else. And what this is a Christian religious art in which there are saints, and this is St. Peter here, and this kneeling figure here is doing something interesting. The thing that the kneeling figure, this guy, is doing is he's carrying, right here, an image of this triptych. So this is another Droste Effect infinite cat thing. It's a recursive image in which the picture depicts a picture of the thing that the picture depicts. It's a recursive image. It doesn't have in the center panel a picture of him. I think this is Giotto. He didn't go that far, but this kind of image of itself thing apparently was something that occasionally would pop up in early Renaissance art. So just so you know, write all that down. It's on the exam. Okay, so there it is, an example of another recursive image. So anyway, my point of this, aside from it being fun to find ancient stuff that embodies the concept, is to also remind everyone that sometimes these ideas, these kind of abstract ideas, in the modern context, they have this kind of practical and engineering purpose, cutting down problems into subproblems. But the idea has been of recursive representation of successively smaller and smaller has been around since ancient times. And I could cite some other examples, but I think we're kind of running out of time, so I'll stop there.